Hello everyone, my name is Alvaro, and in this video I will be solving one of the problems in the Leetcode 75 problem list from Blind. Today we will be doing problem 104, maximum depth of binary tree. This is the first binary tree video that I post of the list in the channel, and I think it's probably the easiest one. So if you want to start working with binary trees and just review your Leetcode skills, I recommend that you start with this one since this is the simplest problem. A tree is just a collection of nodes a binary tree is a collection of nodes in which each node can have at most 2 children, and there are also no loops, meaning that as we go down, we will not be able to go up by unless we traverse back using like the edges that we have previously used to go down. So, what does the problem say here? Given the root of a binary tree, return its maximum depth. So this will be the root, node number 3, since it's the top one. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So, example 1 has this root right here, and the output is 3. So let's see why the output is 3. So here we see that node 9 is at the second level, so the depth of this node is 2. And similar thing with this node right here, which is node 20, the level is 2. As we go down, its children have exactly one level higher, or lower, if you want to call it that way, but I'm saying higher because the number will be 1 greater. This node right here is at level 3, and so is this node. Therefore, overall, the entire output will be 3. So, how do we find the maximum depth? If this is the first time that you've done this problem, maybe pause the video and give it a little bit of thought. So we will continue now. We will use recursion. And how are we going to use recursion? So in order to use recursion, it's always critical to have a base case. So for example, if we look at example 2, there is no image, but suppose that, well, not suppose, this is what this input means. You have a tree with a 1 here, an empty child on the left, and a child on the right with level 2. Level 1 has level 1, the root has level 1, sorry, and the right child has level 2. Therefore, we return a 2. If the root will be by itself, then we would return a 1. And if there will be no root, then we would return a 0. We will use this empty root as the base case. So if we are at a none pointer, at an empty pointer, then we will return a 0. Now, how do we find the maximum depth of the tree? Well, like I said before, we're going to use recursion, and we can think of it recursively. Obviously, the maximum depth of the tree will be either the greatest depth on the left or the greatest depth on the right, meaning that it can either come from the left or from the right, or both, in which case it doesn't matter which one we pick. So how do we know how many, what's the depth at whatever level that we're at? Well, in the beginning, like I said before, if we are at whatever level, we know that we are at least at level 1 or greater, no matter where we're at. Therefore, the depth on the left will be equal to 1 plus the maximum depth on the left, and the depth on the right, the maximum depth will be 1 plus the max depth on the right. So we will pick either 1 plus the greater depth on the left or 1 plus the greater depth on the right. And that will be true. That will be the greatest depth at any node at any point in the tree. So let's write it down now in code. So as I said before, we can say that the left depth is equal to 1 plus max depth of the left side. And similarly, on the right. Now we will simply return the greatest of the two. All right. So before we run this, let's run it manually with this example right here. So the root is not none, so this is obviously 0. And then we will define letDef to be 1 plus whatever this method returns on the left node, on the left side of this node. So we go to 9. And here we do the same thing. The root is not none, so we go both on the left and the right. So letDef will be 1 plus whatever we return on the left and whatever we return on the right. The left child and the right child are both none, since they point to nothing. Therefore, both of these will return a 0. So the left def will be 1 plus 0, and the right def will be 1 plus 0, 1 and 1. Therefore, we return the max between those two. So the max between 1 and 1 is simply 1. And now we're back on the root node. And in the root node, the left def will be 1 plus whatever we returned, which is a 1. So here we have a 2. So think about it. Maybe write it down if it helps you to see it better. And on the right def, similarly, we will go down. So it will be 1 plus whatever we return here. And here as well, the left def, we go, and it will be 1 plus whatever we return here. Now we go on the 15, and it's the left def, 1 plus whatever we return here, and the right, 1 plus whatever we return here. Both of these are null, so the left def will be, for this node, will be 1 plus 0, and the right def will be 1 plus 0. So we return the max between 1 and 1, which is 1. So for this node, the left def will be 1 plus 1, which is 2. Now we go on the right def. We go down here, so right def is 1 plus whatever max def returns in here. And then we go to this node, and just like in 15, the left and the right are non-pointers. So this returns a 0, and this returns a 0. So left def here will be 1 plus 0, and right def will be 1 plus 0. So both of them are 1. And then we return the max between 1 and 1. So right def now is 1 plus 1, which is 2, for this node right here, 20. Now, as we established before, left def here is 2, and right def is 2. So we return the max between 2 and 2, which is a 2. And as we go back to the root, remember that right def is 1 plus whatever we returned here, which is 2. So here we have 1 plus 2, which is 3. And then here we return the max between 2 and 3. So the output is 3. And then this should work. There you go. Now, this is the most efficient solution. And what is the runtime of this? Well, think about it for a little bit. Now, the runtime is O of n because we will visit every single node in the tree at any point. Now, what is the spacetime complexity? Think about it for a little if you need to, and pause the video. Okay, so think of the worst case scenario for spacetime complexity. What would that be? Keep in mind that whenever we're doing recursive calls, we are keeping a stack trace. So think about it as like having a stack in which we're going to keep track of where we are in the program. So when we're doing recursive calls, we actually take up memory space. The worst case scenario when doing these recursive calls would be a tree in which every single node just goes straight, meaning that every single node just has one child, except the last one. So here, instead of having like a 9, we will, let's say we make the 9 the child of the 7, and then we make the 15 the child of the 9. In this case, there will be 5 nodes, and we will go 5 levels deep on the recursion level. So the worst case scenario here will be that we store n elements, n recursive calls. Therefore, the spacetime complexity of this problem is O of n. Make sure that you review a little bit of this if you're confused with recursion, because recursion sometimes makes you misunderstand space-time complexity. You always have to keep in mind how many stack calls you make, how many recursive calls you make at any time, and what is the worst case scenario for that. Alrighty, so thank you very much for watching the video. I hope you enjoyed it, and see you in the next problem. Bye-bye.